All right, good morning. Good morning, class. I am so sorry to have to lecture from here, but I guess you understand. So I think and hope this should be live and set up well. Before I launch into my lecture here, first, again, sorry about Tuesday. And I just want to say that we'll be working to catch up on lost time. You can expect that our first exam will very likely be pushed back by 1 day, one class period. Or possibly what I might do instead would be to just cut out a little bit of the content. But I think for now, let's expect that the syllabus will probably change. Well, it'll change one way or the other. Okay, and if any of you who are here and experiencing this live, I'm not actually sure about the delay between the time you comment and the time I see it. I think on my laptop for class, I shortened that to about 10 seconds. It might be 20 or 30 seconds here. So if somebody, when you log in, I see one viewer now at least, when you log in, if you could just say something in the chat, hello, just to double check that I can see it, I would appreciate that. Okay. All right, so with that, I'm going to go ahead and get going and talk about mass balances. So today we're going to pick up basically where we left off. We had talked briefly about mass balances, starting to think about them, and okay, thank you. And as you see, I've got it set up so you can kind of see the chat here, so that you can feel free to talk with one another. It'll stay there just for a couple minutes and then go away. All right, so we left off just right about here. We were talking about mass balances in terms of how much stuff is accumulating in a system. And we're going to draw a system with something we might call a control boundary, where we have some control over what's going in or out. So control volume or a control boundary here. So then really what we want to know is something about the rate at which things are going in, out, or accumulating. So what we're looking at is rates going in, the rates of anything crossing back out of that boundary, and just so you know, it could also come out a different way, or we could just say it goes out some other way, doesn't join this stream, but it's going out, right? Any of those rates going out, any rates going in, doesn't really matter where they're coming from. We're going to look at the system in that manner. Okay, then we can sum these going in, going out, the reactions going up or down, and deal with our system that way. Okay, so then we took a look at this practice problem here. We had a stream flowing in. I had you guys begin to solve this last time. And so what I'll do with you real quick is work through that with you. So here we have this control volume boundary. We have two inputs. And if we look at the input rate, again, that's probably going to be a mass or maybe a concentration per time. And by the way, if the sound or other settings here are not very good, please do let me know in the comments. I'm happy to adjust, and I have a few things I can do to adjust that. Okay, so in this problem we have essentially two inputs, no reaction, so we were told it's not reactive, and we have one output. So you probably could have intuited this, like I think I mentioned in class, but our input rates will essentially equal the output rates, and we can derive that from our overall mass balance when we say our accumulation is equal to the inputs minus the outputs plus the reactions. In this scenario, we're not really going to have any way for this stuff to accumulate. It's just as two streams mixing and then joining and leaving, right? We're just looking at the area where they're mixing here. So we should have no accumulation of the chloride. Then we have some inputs minus the outputs and no reaction. So that gives us to the in equals out. So you probably could have intuited that, but if we had maybe some reactions involved, or we had a little bit more complicated of a system, our intuition might not give us the full picture right away. So that it's kind of nice to be able to see that what we can do is start from this broad accumulation term and work from there. Okay, so with that, our input rates would be, we can simply multiply the concentration by the flow rate, because what's going to happen is we will get, so we have a mass per volume multiplied by a volume per time yields us mass per time, which is exactly the units we're looking for. Okay, so let's take a look at our input rates. We'll say 20 milligrams per liter times the 10 cubic meters per second. That's input 1 here, CS. We could write this as CS QS plus CW QW equals CM QM. Okay, so when we write all that out, we have this guy plus 40 milligrams per liter times 5 cubic meters per second is equal to the unknowns. Okay, so we need to solve this problem, asks us for the downstream chloride concentration. So we have two unknowns equal to some value here that we can calculate. Even just off the top of our head, we can see 20 times 10 is 200, plus 40 times 5 is also 200, so this is going to be 400. And the units, I'm going to leave them as is for the moment, because when we solve for CM, the flow rate units will cancel, assuming we find the flow rate in cubic meters per second. But if we were to write out the units, they would look pretty funny. They would be milligrams cubic meters per liter, which we could convert liters and cubic meters per second here. So we'll just leave it like that for a moment. And when we stop and think about the QM, well, the water in the system should be conserved. And so the QM should really just be a very simple mass balance. Again, we could do this entire problem on the water first and say, well, we've got 10 plus 5 coming in. Well, what's coming out then? That's actually a mass balance. It sounds so trivial, so silly, almost stupid, but that's actually the accumulation of water is 0. We have some set volume there. It's not changing. So what's coming in is equal to what's going out, right? That we could actually do the same thing. So we could say that QM is going to be equal to QS plus QW. So this should be 15 cubic meters per second. Okay, so that means that all we need to do is divide 400 by 15. Let's do that real quick. It's 26.6 or 26.7 milligrams per liter. Now, we can stop and think just for a moment about where we started. We started with one stream at 20 milligrams per liter. and one stream with a lower flow rate at 40 milligrams per liter. So if they had the same flow rate, we would expect it to kind of just average. So we would have expected 30 as the final if it was 10 plus 10 in terms of flow rate. So the fact that we're below that mark makes sense, and the fact that we don't have some number that's less than 20, because that would never make sense. So you can stop and think to yourself on these questions, does this even make sense? We should be diluting the stronger solution here a bit. We expect that to be diluted because there's a stream with less chloride. Okay, so that's the problem. Hopefully you're able to get that. Again, I know this is probably painfully rudimentary, but what I really want to stress here is that we're going to take a formal mass balance approach here coming from this governing equation that can tell us about pretty much any different system. Okay, that was just some space to work that problem. All right, so let's get into the form with which we're going to describe these mass balances. So what I mean by the form, I'm talking about a reactor of some sort. So here pictured we have an aerated wastewater treatment system. So we've got a bunch of bubbles popping up and just mixing this chamber. And so this chamber will have certain properties. Water is going to be flowing through it. It's going to have an input and an output. But while water is in there, it's being mixed around by all of this aeration. And so that's going to change, in some sense, how long the water stays in one place. It's going to change the dynamics of the reactor. It's going to look very different if you had a very long, narrow channel that didn't have any sort of mixing at all. For that matter, we can call my water bottle here a reactor of some sort. Of course, there's no inputs or outputs normally. We could have a reaction going on in there. Hopefully not. Because hopefully there's nothing bad in there. But we could call that a reactor. So we're going to take a look at a few different reactors. The first and well, not the first. The one pictured here, we might call it continuously mixed tank reactor. Okay, so we'll let's see. Okay, we're going to come back to describing the reactors themselves. So we're going to have three different types of reactors. One would be a batch reactor like my water bottle. It's closed, nothing's happening. One's going to be like that, but with the flow coming in and out. That's what we see pictured here. And then the last one will be more like a hose pipe where you have water at the front's not going to mix with water at the back. So we're going to talk about how to fit, how to properly model those with a mass balance equation in a bit. But before we get there, because this is really getting to applying the flows and adding some sort of reaction somewhere. Before we get there, I want to talk about the reaction term that happens inside the reactor. So we will come back to reactors, but let's focus first on the reactions. Okay, so first and foremost, I want to say that the reactions themselves do not care what reactor they're in. The actual reaction term in a mass balance is right here. And the reaction term is, you might say, agnostic to, or doesn't care at all about what it's in. You could put some reactive substance, maybe chlorine, in my water bottle, or you could put it in a toilet, and that chlorine is going to react the same regardless of where it is. Now, it might be important how long it has to stay there to do the disinfection or whatever. But the way we describe it, the reaction term itself, does not matter about the reactor, because the reactor stuff will be accounted for right here. So we're going to say this is independent of the reactor. So keep the reaction itself separate from the reactor. The reactor is just a container. Okay, so talking about reactions, you've probably seen this before somewhere, but in case it's been some time, we typically deal with a few different reaction orders that we could describe. And this is really describing the rate at which something's changing. That's a reaction. But how does that rate depend on how much of this stuff you have? For example, if you have a bank account that has interest, maybe it's a loan and you're paying interest, maybe it's savings and you're gaining interest. The amount of money you gain or pay is dependent on how much is there, what your balance is. So if you have a savings account that has an incredibly high return of 10%, but you only have $10 there, and let's say it's 10% per year, then you gain $1 in a year, right? Whereas if you had a incredibly low interest rate of 0.1%, but you had $1 billion, you're going to be making a lot of money in that year. So it depends on how much stuff is there. That's called what we call a first order reaction. Now, if you have a bank account and you just happen to put $20 a month into it, that would be a zero order reaction, if we were going to call it a reaction, because that's a set amount. It doesn't depend on how much is in there. It's just a flat amount every so often. So that's the type of the way to think about the reaction order is kind of in that manner. So if we were to take a look at reactions changing a concentration as a function of time, we can write the rate equation as some rate is equal to the change in concentration per change in time, so dc dt, is equal to either plus or minus, depending on if it's a growth or a decay reaction, times some rate constant k, times our concentration c to the nth power. And n here is our reaction order. So now we should be able to see that if we had a zero order reaction, the way that would write up is dc dt, and let's call this one a decay reaction, would be equal to negative c to k, some k that will give us a slope, times c to the 0 power, and anything to the 0 power is just simply 1. So that c goes to 1, so we could write this as just simply negative k. All right. So that means that the dc dt plot here, if we plot c versus time, would just look something like a negatively sloped line. And let's assume that was a linear drawing. So then in the case of a first order decay, still have dc dt equal to negative k times c to the 1 power. So this is just equals negative k times c. So here it depends on how much we have in there. So if we start with a lot of stuff in there, let's say we start up here, the change in some step of time is going to be larger than once we've decreased it a fair bit, right? So try to draw this a little more smoothly. Something like that, right? So the change in C is decreasing because we have less C there. The smaller the number of C, the smaller the change per unit time. So then in a second order case, and this would be, by the way, 0th, 1st, and 2nd orders. This one is going to have the same type of situation, dc dt equals negative kc squared this time. So here, it's just the same concept here, but dramatic. And then once we get to a particularly low spot, then we get a kind of a sharp bend and then approach. Then we approach 0. All right. Now, each of these, of course, could also be drawn with a growth equation, and it would look something more like this. And of course, these would be kc squared, kc, or equal to k, right? So we could have plus or minus. Okay, is that clear? Does that make sense? You're welcome to comment, ask questions at any point. I hope you feel free to do so. Okay, so let's talk a little more elaborately about each of these. I just drew them up for you, but I'm going to do a little bit more drawing to give you some attention to what happens when we might need to integrate these equations, or what happens if we take a derivative. You'll understand why as we move forward here. And the other thing I want to highlight with these are the units, because sometimes you'll get a word problem with a description that implies some rate constant, or gives you some information about the rate constant, but you won't necessarily know what order it is. But you can find the reaction order if you know the units. So a bit about units here as well. For a 0 order reaction, we have, again, dc dt equals plus or minus k times c to the 0 power. So this is basically plus or minus k. And if we take a look at the units that must exist to satisfy dc over dt here, equal to nothing over on the right except for k, then the units for k have to be the same units as dc dt, right? So the units here would be concentration divided by time. So let's call it milligrams per liter divided by seconds. Those would be the units. We could rewrite that as milligrams per liter per second, right? Milligrams. Excuse me. Okay, so this is, in this example, we might have other types of units, but it's going to be a concentration per time. In this example, we have milligrams, liters, and seconds. And so when we plot that for, could be decay or some growth reaction, we're going to just plot the decay for the moment. A lot of our systems will be looking at decay reactions, not all the time, but that's going to be pretty typical, or a little more common, so I'll use those typically as an example. So when we integrate to, say, or excuse me, take the derivative here, we have a plot of c versus time, and it's linear. So if we take the derivative of that, you'll remember from calculus that the rate at which it's changing is not changing, right? Because it doesn't depend on, the rate at which it changes doesn't depend on concentration or time or anything. So over time, it should just be a flat line of some value. And in this case, since it's a negative value, this would be a negative value. So negative something there. All right. Let's take a look at first order reactions then. So here we have, again, dc dt equals negative kc to the 1 power, or positive kc. So c is a concentration here in milligrams per liter. Time is going to be seconds. And if we take a look at the units that have to satisfy, that's the question, right? We know the units must be concentration per time. So we'll call this milligrams per liter per second. Have to be equal to milligrams per liter per second. And the question is, what are the units of K? And so we have the units of K here times a concentration unit. So therefore, the units of K have to be 1 over seconds. So this would be our 1 over time. Now, when you're working with this at first, it might feel a little bit confusing or just sort of weird. My stuff is changing, but my units are just time. Like I've got kilograms of this stuff that's changing. Why is the units just time? Shouldn't it be some certain amount per time? But actually, the truth of it is, you've seen this type of rate all over the place in your real practical life. Because if you've ever taken a look at, again, some sort of financial system, whether it's banking, investments, or maybe a mortgage, you'll see advertisements all over the place for, X% APR. So from finances, you'll see, I don't know, 1.5%, things like that advertised, right? So what they're talking about, or APY, is it? It's probably APY. Annual percent yield, I think. What they're talking about is some number here, 1.5%, so that's referencing the amount that's there right now per year, or the annual part is telling us per year. So this is just really some number with a year to the -1 unit. That's actually all it is. And what it's referencing is, you have some bank account or mortgage amount or whatever it is, and the interest rate or the yield is going to apply some fraction of it and add that every year. That's really all we're talking about. So you've actually seen this all over the place. So when we work with it in our word problems here, when you see a per second time, you'll recognize this is a first order reaction, because the units have to satisfy this value. So if you ever get confused on the units, come back to the simple expression of what is a rate. It is something changing over time. And then what we're going to do once we get back to the reactors is put that rate in the context of the reactor. So then we add in parameters such as the volume or the flow rate, things like that. All right, so we showed earlier this should look something like this. Now if we take the derivative of a first order reaction rate, we will be able to see that the rate at which the concentration changes over time should be a linear line. So just going basically straight back to calculus, you've seen this kind of stuff before in physics. This would just be what it's looking like if we're considering it for the amount of some chemical changing in water, is kind of where we're taking it in this class. Okay, second order reactions, we're not going to use these very often, and the math gets a little bit more difficult to use them, so we'll keep them relatively simple when we do encounter them. But you should be able to see it, distinguish it, and understand kind of what's going on. And to be honest, there are not too many cases in the real world where we have second order reactions. When we do have them, they happen so fast, they typically will consume everything that they are using. Or perhaps it's a system like up in the atmosphere, we have certain photochemical reactions creating, destroying, generating ozone all the time. Happens, it's just a dynamic circulating system that kind of keeps going and going. Okay, so for a second order reaction, again, the same principle applies. We need to satisfy milligrams per liter per second. Now we have this K, and then over here we have milligrams squared per liters squared. So how do we deal with that? In order to get just milligrams per liters, well, we need the inverse. So K is going to be the inverse of a milligram per liter, so a liter per milligram, and we need the time, so we're going to add in time there. So really we're just filling in whatever we needed. So with that, we will get the required situation there. So the units for a second order reaction look a lot like the zero order reaction because it has liters, milligrams, and seconds. But if we flip back, we'll see that here it was milligrams per liter per second, whereas the second order equation is liters per milligram per second. All right, so that's how you know what these things are going to look like. Again, this graph here is going to be quite sharp, and then it's going to be an exponential on the integrated, and we could integrate that one step further, get to linear, one step further, get to the zero slope. Okay. So that's kind of what I wanted to say about the reaction orders. This is how you find the units, and so this should help you navigate when you have a system where you're not sure, okay, what order, how do I need to write out my rate equation in order to put it into a mass balance. That's where you should go to think about what are my reaction orders, and that's going to tell us how to assemble the reaction term of our mass balance. Okay, so now that we know something about the reaction term here, now we're going to put that into a reactor. So we have three ideal reactors that we're going to talk about. Probably won't spend time, especially given our two canceled classes now, discussing non-ideal reactors in this class, but certainly no true reactor in practice is actually going to be very close to, well, it should be close, but should not be truly ideal, because we will assume something like perfect mixing, but that's not necessarily reality. All right, so with that, the three ideal reactors that we can get close to and that are very useful for modeling would be a batch reactor. That's my water bottle here. I can mix it all around. I can put something in it that reacts, give it some time, and treat one batch of water that way. Washing machines often work this way. They'll fill it up and not have anything flowing in or out, and just have the reaction going for a little while, and then it will drain. So you're doing a batch of laundry at a time, and it's doing a batch washing, and then it'll drain it, and then fill it up to rinse it, and then drain it. So that would be a batch process rather than a continuous flow. The second one would be what I will call a CSTR, or a continuously stirred. See if I can spell with my COVID brain today. Continuously stirred. Some people will call them a CM, sort of continuously mixed. You'll see them sometimes continuously mixed flow tank reactor, CMF STR, or CMFR, something like that. Anyhow, our book, he uses CSTR pretty often. This is a common one. Continuously stirred tank reactor. It's basically you have a batch system and you are sending water in, and it's also going out at the same time. So it's basically a batch reactor with a hose going in and a hose going out. Now, a plug flow reactor here on the right is going to look a bit different. And again, the reason here is because in a continuously mixed system, when you add water or solution at all to the start of it, as soon as you add it, we're assuming it's all completely mixed. So that is immediately diluted throughout the entire reactor. And so whatever you add in the front is immediately a tiny part of that should be going out the other side, or a small part of that. So that's a lot different than if you had a hose, and if you've ever turned on a hose in the summer and it had water sitting in it, it's going to take a minute before you get cold water or cooler water, and water is going to be actually coming out pretty hot because it's been sitting there baking in the sun for a little while. So that would be a plug flow reactor, where you have a plug of your liquid flowing through your system, and it's going to take some time before it exits and reaches the end. Okay, so let's talk about how to assemble our mass balance given these different reactors. So for a batch reactor, we have no inputs and no outputs. So in terms of actual flow, it simplifies things a bit. So this will go to 0 and this will go to 0 because we have no flow across our control boundary by definition. We're going to assume that a batch reactor is perfectly mixed. That's pretty typical. I guess you can make a non-ideal reactor and add something and have a not mixed system if you wanted to, but for an ideal reactor, we're going to have a complete mixing here. So that means that if you look at what we just did, the accumulation, whatever accumulation is happening in that vessel, has to be equal to the reaction that's happening in that vessel. So that means we are never going to run a steady state batch reactor, because the steady state assumption was that a steady state system happens when accumulation equals 0. So that means that if we have a steady state batch system, nothing's happening at all. There's nothing interesting about it. So we'll say batch systems I guess are not at steady state, unless we have multiple reactions and they're counterbalancing each other. That would be the only time we'd reach a steady state in a batch system. Unless positive so the reaction term here, and that's a probably a good thing to note here, we could write it as growth, so we'll say plus the growth reactions minus the decay. So if we have bacteria growing but also dying, we could write it that way. So we could reach a steady state, I suppose, but typically if we have something happening that's interesting, we probably would write it. We probably would not assume steady state for a batch reactor in most cases. Okay, so anyway, let's write out the mass balance. So accumulation equals the reaction terms. So what we'll say is the accumulation within some volume, if we give this some volume, we write the accumulation as dc dt. The reason we write it that way is because dc dt is the way to write accumulation, right? It's a change in our mass, or our concentration in this case, over time. That's accumulating, whether it's negatively accumulating or accumulating positive like we normally use the word. And it's going to happen in some volume, which, again, let me remind us that our rate terms are always going to come back to a mass per time value. So whatever our reaction term looks like should end up as a mass per time. When we did the flow rate times concentration, this is a volume per time, let's say, or let's just say volume per time and a mass per volume. So this yields us a mass per time, right? So whenever we're doing these terms, whatever we put in them has to get us back to a mass per time. So volume of our reactor times the concentration that we're interested in divided by time, that's an accumulation term, mass per time. So V dc dt is going to be equal to the reaction, and here we could say plus kc to the nth power in the volume minus kc to the n value in that volume. And here I'm going to say k growth and k decay, just to differentiate, to suggest maybe we have one of each or something, but we could very well just have a simple case for a first order decay would look like this. V dc dt equals negative k times c to the 1 power times volume. And that would be our entire mass balance equation. Okay, so we're gonna take a look at the math a little more closely in a couple minutes, but I wanted to show you the process of taking this broad equation and delineating exactly, okay, what does this mean as a rate term, and why do we arrange things the way we do. Okay, so that's the batch system. Again, let me know if you've got any questions here. All right, for a continuously stirred tank reactor, a CSDR, we're again going to assume perfect mixing. We're also going to assume a continuous flow in and a continuous flow out. Now, mentioned earlier that we could have two different flows coming in or multiple flows going out. It's not necessary. Most of our systems are going to have just one in, one out, but it doesn't actually change things too much if you add some other ones. So just keep in mind that what we're looking for is a term that encompasses anything coming in across the boundary, a term that encompasses anything going out of the boundary, a term that encompasses any reactions that are happening inside the boundary, and all of that, we could get some accumulation. So again, we'll say we're at steady state if the accumulation equals 0. But how does it look like if we put in a reaction here? So let's again give this some volume for this reactor. Our accumulation term should be V dc dt, just like in the batch case. That doesn't change. We have some volume. We're interested in the accumulation within that volume. Now here we have the flow coming in, Q, and a concentration coming in. We'll call this C naught coming in and C going out. So in this particular system, that's coming in. What's going out is Q times C. And then our reaction, this time, let's just go ahead and say, for the sake of example, I talked about we could have multiple reactions, but for the sake of this example, for our reaction term, let's do a second order growth, just to show you what that would look like. So since we have our other term is a growth term, we're going to have plus V times some rate constant K times C to the second power here. But when we think about C, it's going to be the C inside here. Because this system is perfectly mixed, whatever is inside here is the same thing that's coming out. So we actually would draw our C inside here. So give it a K as well. So that means as soon as our water arrives at our system, we now immediately have a change in concentration as soon as the water hits the reactor, because it's effectively diluting it. Now, it's kind of an odd system because our plan to treat the water is to let it sit there and remove the concentration C to some extent here. So anyway, we'll talk more about that later, but it's the fact that it immediately dilutes means that the C inside here is also the C coming out. All right, so this would be our example for a second order growth equation. And again, if it was steady state, we set all this to 0, and then we say that's, then write the rest like normal. Okay, so that's batch reactors, plug flow CSDRs. Now a plug flow reactor, or a PFR, we have mixing, but only within one plug. So our assumption here is we have continuous flow into our reactor. So we'd have flow coming in and a flow going out. But we only have mixing in one slice of our plug that is going through. So within one really thin slice that we can imagine this being perfectly well mixed, but it is not mixing downstream. There's no mixing that way, right? There's no lateral mixing in an ideal plug flow reactor. So what happens in that case, we'll just write it that way, is that it's essentially like we have a little tiny conveyor belt. and a little tiny batch reactor on a conveyor belt that's going to spend some amount of time in the plug flow reactor with a reaction going on inside of it, and then it's just going to dump out on the other side of the plug flow reactor. So when we take a look at, this drawing is from one of our online books, and we take a look at, this says T equals tau, where in this case tau is often used the same way we will use theta, which is hydraulic retention time. So in what we're saying then is the water spends some amount of time in the reactor and then it leaves. So at 1 tau, 1 theta, that means it spent exactly 1 residence time, right? That's the definition of how long it takes to do that. And remember, as we talked about last time, our theta is going to be V over Q. So if we have a low flow rate, that means our residence time increases. If we have a small volume, our residence time will decrease. Okay, so in this situation, the math actually becomes pretty simple, because what we can do is say, well, for an accumulation term, if we treat it as a batch system, then it's a batch system that really we don't have anything going in or out of our plug, which is the batch. So we'll have 0 minus 0 for the input and output, plus our reaction term. This could be a minus, so a plus a negative reaction. But when we solve it, we're going to solve for T equals theta. So that'll be the big difference. We have some amount of time for this batch reactor to occur, is the amount of time it takes for the water to go through the reactor. Rather than me keeping my water bottle for some amount of time and then emptying it out, instead I will be continuously flowing the water through the system, and that water just has some amount of time as it snakes through the plug flow reactor. Okay, so that brings us to our definition of hydraulic retention time. So this is going to be a key design parameter. I've talked to you about it twice now already. Theta is V over Q. Again, commit this to memory. You will not be sorry. You'll be happy you did. Where V is a volume, Q is a flow rate. And in order to get a good idea of what these typically look like, let me see if I can pull this up on my browser for you. Just a moment. Okay, so here's an example video of what we would call a tracer test. Where we've got water flowing through this chamber. We've got a dye in it to kind of show us what's happening, and this this is kind of simulating a plug flow reactor that has water flowing through, and you can see when the dye reaches the other side, it has taken some amount of time for the water to travel through. It's also a good demonstration of why and how some things are not actually ideal. You can see some areas are not really mixed. So in a plug flow reactor, it should be completely mixed in some plug. across the system, but we see some pretty big gradients forming just because the natural occurrence of how all that works together. So we're seeing some non-ideal characteristics, maybe some areas where some dye is going, some of the water is just simply moving faster than other pieces of the water, some areas that are not mixing at all and are just sort of dead zones. The water's, no new water is ever seeing that spot. So tracer tests like these can give us a lot of good information on reactors in real systems, in reality, how well are they functioning. But overall, the general shape is it's kind of a plug of water flowing through here. Okay. I don't know why that would put. All right, so the tracer test stuff is a good example, a good field of study if you're interested, but for now we're just going to leave it at that. Okay, so let's, I kind of mentioned these briefly, but I want to go through how we practically get to an equation that we can use from the broad mass balance equation. So this is going to require a very quick and simple refresher on your calculus. There's pretty much one little trick from algebra and one little trick from calculus that you need. You'll remember them as soon as I show you them, and then you'll use them for these derivations in our class. Okay, so let's start with the batch case and derive a mass balance equation from the big picture of the accumulation as the input minus output plus reaction, and take two different equations here, or scenarios. So a zero order decay and a first order decay. Now, if you feel like practicing this on your own and seeing if you can get this right, you're actually welcome to pause the stream, pause class essentially for yourself, and see how that goes. Now, if you wanted to ask questions more in live time, of course you probably won't want to do that, but just a thought in case you wanted to do that. Okay, so here we have a zero order decay, and so we would start by writing that to say our rate term itself is equal to dc dt equals minus k times c to the 0 power. Now for our mass balance, what we would look at here is in the reactor, V, the accumulation dc dt, is equal to our reaction term in the volume. Again, we could put in a 0 minus a 0 for the inputs and outputs, because those we don't have any in a batch system. And then we have a decay reaction, so our reaction term is going to be a negative in that volume V K C to the 0 power. So what this will simplify to is V dc dt equals negative V K C to the 0 is just 1. So we can get rid of the volume terms here, and now we have dc dt equals minus k. So if we take the integral, let's move the dt to the other side, so it's dc equals negative k dt, and we want to take the integration of either side here. We can go from time 0 to time t, and for here we would go from c initial, c0, sorry, to some c final. Would look like that. Then we integrate, right? So we, on the left side, we have simply c minus c initial, and on the right side we have negative k times time, because this would have been k times time minus k times time initial, but that initial time was 0. So this is our derivation. Now we can, when we derive a mass balance like this, we can solve it for whatever we need to. I guess the most common thing would be to solve for C, so we might put this in terms of C to say C equals C naught minus KT. Now, a zero order decay batch system is a very intuitive system in terms of you probably could have thought to yourself, oh, if I have a case where I'm subtracting $20 from my bank account every month, I started with $100, 4 months later, I have $20 left. You could see, if your question is how much money do you have left after 4 months, that's C. C naught was your initial starting point, that was $100. Your rate was $20 per month, and your time was 4 months. That all works out and is just so stupidly obvious that it's like, why did I need any integrals here, right? But the process here can let us handle much more advanced systems. So for example, we'll move on to the first order decay. In this case, we have the same setup, right? We want our V dc dt. That's going to be equal to inputs minus outputs, none of those. And our example case here is first order decay. Another tip here is I suggest you do this, the same exercise with on your own for growth equations, just to prove to yourself what this looks like if you do it that way. All right, so V dc dt equals negative V times K times C to the 1 power. So now we'll cancel the V's again, and we have dc dt equal to negative Kc. So now when we separate to integrate, what we'll do is we'll take dc divided by c to get the c's as like terms on one side, equals negative k dt. So the right side of this equation, when we integrate it, it's going to look exactly the same, which is very nice. And when we integrate this from C naught to C, what do you think? What is dc? What is the integral of dc over c? Here's the spot where you've seen it before. You've seen this one, and you've done it probably 100 times back in calculus, because the integral of 1 over x dx is the natural log of x. So you've seen that before. That's actually a pretty common one, and all you need here is a reminder that that's what we're looking at. We will see this formulation a lot in this class, so remember that exists, and that here's where it can help us. So when we do that, what we get is the natural log of c minus the natural log of c naught equals minus kt. So that was the one calculus tip, trick, whatever you want to call it, relation that we needed to remember. Now there's the one algebra relation that we need to remember. From algebra, we could recall that when we have two logarithmic terms and we have a minus like this or a plus, we can actually combine those and say this is the same thing as writing the natural log of c divided by c naught. That's, like I said, just algebra thing. So if you remember that, and if you get this thing here, this equation is about to become very, very familiar because we've seen it in many scenarios in life. So from here, we can get if we wanted to simplify, again, if we want to solve for C, maybe you don't need to solve for C, maybe you need something else. At this point, once we have it kind of integrated, it doesn't matter to me what you're solving it for, so long as you're solving for what you need. Maybe you solve for K. And in fact, it would be easier here to just go ahead and divide by negative T, and then you find your K. So you're going to have to do this with mass balances. I'm just showing you a mass balance process that gets us to a typical endpoint. But the whole point of a mass balance is to solve for whatever piece you need within it. Excuse me. So the other algebra thing we can do here is, if we want to get rid of the exponent, we can raise e to the power of both sides. So e to the ln of c over c naught and all that. Negative kt. And when we take e to the power of a natural log, that essentially just cancels out that natural log. So we have c over c naught equals e to the minus kt. And if we say get rid of, move the c naught to the other side, this would be c equals c naught times e to the minus kt. Now, if you ever learned from algebra how they called it the PERT equation. For me, your principal value is going to be equal to e to the rt, right? The PERT equation, talking about how much money you're going to make after some number of years given some interest rate. So it's a first order equation. In this case, the PERT equation is a growth equation, and what we just derived was a decay equation, but I think you can see how we actually derived that equation you learned way back in Algebra 1 or whatever. So that's our mass balance. Excuse me. And hopefully you can see that. And this is the type of derivation, this is the level of calculus and algebra that you need to remember in order to do truly the mass balances in our class. There's a couple slightly more complicated things if we get into second order systems, but if we do that, you'll have a lookup table to reference to remember the relations for an integral that's more complicated than this. But I'm going to expect that you can do this and you can know this for yourself. All right. So I have a note down here that my notes are a little bit in the way, but essentially if you did the same thing for a plug flow reactor, everything would be the same, except instead of solving for a T here, you could solve it for theta, right? So theta would go in for T, and that gives you some way to connect it with the actual size and scope of the reactor, because theta is equal to V over Q. But otherwise, the same exact principles apply. It's because we can just assume that we are dealing with that little plug that's flowing through like a batch reactor. There's some other ways to derive the plug flow reactor that gets to the same exact condition. We're not going to get into that today, but essentially you could, instead of looking at it like a conveyor belt system, you could look at it like there's a million, like an infinite number of these little tiny slices, and each of them are a continuous flow reactor that they're mixed in perfectly. And then in that way, if you take a million of them, a million of these CSTRs, you end up with the same math as a batch reactor on a conveyor belt. So either way you go, you get the same outcome. So with our remaining time, I want to go over what it would look like for a the CSTR case, so in this time, our inputs and outputs are not 0. What I will say is, let's assume for the sake of this portion, we will assume steady state in these systems. Now, we don't have to make that assumption. It's not always going to be true, but it's going to be the typical assumption for the typical CSTR. Maybe something interesting happens to our reactor, our process, and then we have something else happening that we weren't expecting, but this would be the typical situation. Okay, so a zero order decay reaction, our rate term is dc dt equals negative kc to the 0 power. So how do we put that into our overall mass balance? Well, we'll start by writing the accumulation term. We will assume this goes to 0, but let's write it out first. Then we have, and by the way, whenever you start writing out a mass balance, I highly recommend you make your own little sketch. So I didn't have a drawing here, so I'm going to draw something to show myself what's happening. We have a flow coming in, a flow going out, some volume, some reaction happening. We have some concentration C. C is also leaving, and some concentration C coming in. So there's a question, do we have to remember the process to get to the final equation? Or just remember okay. That is a very common question. I'm glad you asked. I want you to know how to get there. You will do a lot better on your exams and in the work in general for this class if you understand the process to get there. If it helps you to memorize the final formulation of, let's say, one of the common ones, and you'll see the formulation will change a little bit if we change something about the system. It might help you to know the common terms, but what happens if you have a problem where instead of having just one input, you had two different inputs? Can you derive something then? You'll be close, but if you don't know the process of how to get there, you're missing out on quite a lot. So really, my opinion is that you should know the process, learn the process, and work hard on that. The rest of the class will be simpler for you if you do. Great question, though. Okay, and I will highlight a couple of these that, the first order decay for a CSTR, you'll see that particular one a lot. So that one of all cases might make sense to remember as a kind of tool to help you to make sure you're on the right track. Okay, so for this zero order decay, we have water flowing in, some reaction happening, water flowing out. So we'll have QC naught minus QC minus this, in this volume, K times C to the 0 power is just 1. So we're going to get rid of that. Okay, we assumed steady state, so that means this is going to be 0. So this will be QC naught minus QC minus VK. All right, so this one becomes pretty simple. If we're solving for C, again, you could solve for Q here if you wanted to, but if we're going to solve for C, we're going to move that term to the other side and get Q times C equals QC naught minus VK. So C equals QC naught minus VK over Q. Now, one thing you could do here, you might notice we could simplify it a little bit and divide everything by the Q there, and say this is going to be equal to C naught minus, what have we learned about V over Q? That's theta, right? So minus theta K. So either term would be pretty handy. This would probably be the more common way to see it. Now, for a first order decay reaction, we'll do the same process. V dc dt equals QC naught minus QC, in this case minus VKC to the 1 power. Again, if we assume steady state, this will be 0 equals QC naught minus QC minus VKC. Now we have C's in 2 different spots, and up front we have a Q or a V in every term. So I'm actually going to go ahead and divide everything by Q here to just simplify things a bit. So this will be 0 equals C naught minus C minus the V over Q is theta times KC. So I'm going to move the C terms to the other side. So C minus theta KC equals C naught. And then extract the C, 1 minus theta K, and solve for C. And again, like I've been saying, sometimes you don't want to solve for C exactly. Another common thing that you might want to solve for would be maybe the ratio of C divided by what you started with, right? So this would be 1 over, and I just realized I think I have a mistake somewhere, because this should be 1 plus theta K. So I actually did just what you were talking about. You know, I have in my memory what this equation should look like with a plus here, so I know that I did an error with my addition. So when I added the C over to here, that was fine, but then I added it without adding this part. I somehow did not, I subtracted this from this side, or I did that wrong. So this should have been plus. So my apologies for that mistake. And because I did commit it to memory for teaching it so often, I did catch it. So maybe it's not the worst idea to remember it. Okay, so I'm gonna wrap up in just a moment, but what I really want to highlight here is that these are derived for specific scenarios. I really do want you to learn this process. This is most of what the class is about, is adapting and applying this type of process to different systems. Not every single case has this type of mass balance, but a lot of them do. And this is a very critical skill for most of environmental engineering, to be honest. So I definitely want you to learn it. It's going to take some time, always does take a time to be thinking this way and developing mass balances in this manner. This is probably the most common form you will see and need in our class. But again, I really think that you'll do yourself a favor by going beyond and really getting to know the process I just went through. So do it on your own time with a growth equation. Prove to yourself how that would change it. Try it out with a growth and a decay equation, right? You could say you have a first order decay and a 0 order growth, and see how that would look, right? You're not always going to have this simple case. Okay, we're going to pick up here next time with this practice to put that show an example of just that. Feel free to work on this on your own. The blank slides should already, they should have been there for you already. So I hope you're able to follow along there if you'd like to. And I'll post these momentarily. So, okay. Tuesday, I do plan to be back. I'm feeling pretty good, slight bit tired and foggy headed, so apologize if that disturbs today. But I don't think I'll be any issues coming in on Tuesday next time. So thanks for joining online. I appreciate you guys asking a question and saying hello.